Professor Karem Sakallah is from University of Michigan. He received his bachelor degree in the American University in Beirut, and he did his master and PhD in Carnegie Mellon University. He has many professional activities. The one that caught my eyes is that he established a computing research institute in Qatar. Karem's current research is focused on automating the formal verification of hardware, software, and distributed protocols. He's a fellow of III and IEEE and the ACM, and a co-recipient of the prestigious Computer-Aided Verification Award for fundamental contributions to the development of high-performance Boolean satisfiability solvers. Personally, Karem and I met a few months ago when we were considering working together on an NSF AI Institute proposal. This didn't work out for now, but we discovered on a personal level that we are from the same corner in the world, from the same corner in the Middle East, Israel and Gaza, which led to interesting conversations. So with that anecdotal story, welcome, Karem. Please go ahead.
Thank you very much, Rina. I really appreciate the invitation, and I hope that we will collaborate sometime soon in the future. And thanks everybody for tuning in. I was trying to figure out what to talk about today, and it took a while for me to settle down on this topic here, which is accidental research. And what I mean by that is, trying to work on some proposal research that you've written, and then you discover that that problem is not really all that interesting. Something else that came along was a lot more interesting, and you spend time solving that other problem. So I don't know when or how I stumbled on this one-page essay with the provocative title of The Importance of Stupidity in Scientific Research, but it struck a chord with me, and it's now required reading for all of my students. This is kind of the gist of it, okay? I suggest that you take the time to find it and read it. It's very eye-opening. It's very provoking. It says productive stupidity means being ignorant by choice. Focusing on important questions puts us in the awkward position of being ignorant. One of the beautiful things about science is that it allows us to bumble along, getting it wrong time after time, and feel perfectly fine as long as we learn something each time. It's learning that is at the core of doing research. So what was I doing back when? I was doing this. I was doing low-level timing analysis, of technology, CMOS, then gallium arsenide, then something else. And we were doing timing analysis. I became kind of famous for being the guru on timing analysis of chips. But then we got to the point where we had to solve problems on not just individual gates or transistors, but on an entire chip. And the question became, what is the maximum delay in a circuit like this? So this is a circuit that has a bunch of gates. Let's assume they have unit delay. And you're asked the question, what is the maximum delay from the input X1 to the output Z? I don't know if you studied OR like I did, but this is an application of the critical path method. We can very quickly identify the critical path in the circuit, and its length is 7. So ignoring logical constraints, you say the delay is 7. However, this is not a bunch of delay boxes. These are logic gates, ands and ors in this case. So if we include the logic into this analysis, if I want to go from X1 to A, I must set X2 to 0. Otherwise, the transition on X1 will be blocked. And then to go from A to B, I need to set X3 to 1. From B to C, I need X4 to 0. As you can see, I put zeros and ones on the inputs of ands and ors. From C to D, I need X5 to be 1. And then to go from D to E, I need X3 to be 0, but X3 is already 1. So that means I cannot proceed. That means this path is so-called, so the delay is not going to be 7. It's going to be, I have to go the other way from D to G, and the delay would be 6. that pass on the top that got the do not enter is called a logically false path. So we were doing low-level timing analysis, and then my student came up with this situation, and he says to me, and this is kind of almost verbatim the conversation, is for timing analysis to be accurate, we have to check logical consistency of circuit paths. We need a set solver. At that point, my knowledge of set solving was, I knew about them. So I said, okay, go find yourself one and let's finish this project. He came back and he says, no existing set solver can solve this problem because it's too big. Our circuits back then had between 10,000 and 100,000 gates or variables. He said, there is nothing out there that can do this. So I said, okay, what do you suggest we do then? He said, we need to develop our own solver. And I said, you gotta be kidding, right? You know, I'm funded on timing analysis, and this problem, we're gonna go from 50 to 100,000 in, you know, in a few months. He said, I'm not kidding, I think we can do it. And so we spent a year, at the end of which, in 1 year, he actually finished doing this work. He had started doing this 5 years earlier, but the timing, the set solving was done in essentially 1 year. And so we published, so this was 95, we published in 96 the first paper on grasp, another one in the same year, and then the journal paper in 99. Okay, so at that point, we are, you know, I'm now enamored by this. I like it. I love it because it's so simple and so easy. And so I'm going to show you just what the big idea was. And it's a simple idea. So here is a CNF formula, a function phi that has these clauses. And I'm going to use a color code for the literals. So red means 0, green means 1, and yellow means it's neither. Okay. So here A is assigned to 0. So when it appears without a complement, it's red. With a complement, it's green. B is green, means it's assigned to 1, and not B would be false. And C and D are unassigned. And the same color scheme can describe the status of the clauses. So red means violated. Green means satisfied. And if you don't have green, you just have a combination of red and yellow, it means it's unresolved. So how do we solve this problem? So this is the classical Davis-Putnam, Loveland, and Logman algorithm. I have 8 clauses over here. I put them kind of vertically here to emphasize the fact that we're essentially solving a simultaneous set of constraints, a conjunction. There's a conjunction over here. So you go by picking a variable, making a value, putting it to a value. So here A gets to 1. Some clauses get satisfied. Other clauses get shrunk, the ones that have not A. Then we pick another variable, we assign it, and so on. You know, this is backtrack search. We get to a point now where clause 7 now has 2 red literals and 1 yellow. That means it's unit. And the only way to satisfy it is to make that literal true. That means D becomes false. So I'm starting to draw here what I call an implication graph. B being true and C being true implies, because of 7, that D must be false. And then that gets propagated in 8, and we get a conflict. So this assignment is a conflicting assignment. Or when we built on, when we started doing this, we were reading truth maintenance systems. They called that a no good. I didn't like the word no good. I said, let's call it a conflict. It's a conflict. So we backtrack, and we try the other, values of C. We get another conflict, and you see, so we're doing this. I'm just going to speed through this to show you that we are systematic, and we can find all possible assignments if we have to, that will either show that the problem is satisfied, which in case it is, which in this case it is, or if there is no solution, we prove unsatisfied. That was the standard or state of the art back then. This could not solve our problems. So what solved our problems was to start the same way. But then when we get the first conflict, we say, wait a minute, before you backtrack, can we do some analysis to figure out what went wrong? Because we made some arbitrary assignments over here, and we got a conflict. It's like, you know, you walked yourself into a corner. Why did that happen? So in this case, it's a very simple situation. What happened here is that the assignment of B and C to 1 were responsible for the conflict. D was not responsible for the conflict. B and C were responsible. So we know that B and C is a bad assignment. So BC implies the complement of the formula. By contrapositive, the formula must then imply not B or not C. And we call that a learned clause. We just learned a new fact that is implied by the formula, that if we had it before, we would never have made the assignment to C equal 1 when B was equal to 1. So we add this clause, and at this state of the search, it is violated because B and C are true. But when we erase the assignment to C, it becomes unit. And now it implies a value on C. It makes C become false so that the clause becomes true. And you proceed. So here's another situation where now A and B are causing the conflict. We do the same thing. We learn not A or not B. We then proceed to add a clause not A or not B. It's unit. We then imply B from A, and then we continue. We got another conflict. And finally, the culprit in all of what we have done so far is we just discovered that when we set A to 0, to 1, I'm sorry, we get a conflict no matter what we do with the other variables. So we learn not A, okay? And that is basically the gist of what conflict-driven clause learning is, okay? So if you continue this one here, we're gonna find a solution, okay? It's a very simple idea. And it's really not different from no good recording and remember, adding constraints, except the fact that the things that we learn are of the same type as the input. So what you learn is of the same form as the input formula. It's a clause. There's some regularity in this process. Now there is more than this, as we go along. But here I'm showing in the second row how many decisions and how many conflicts we ran when we ran this DPLL, which is what we're going to call branch search with implications, or so-called Boolean constraint propagation, and with conflict analysis. So we get fewer decisions, fewer conflicts. The first row is if you don't do BCP at all, which is kind of a bad way to go. This is a simple example, but in larger examples, things are way better than this, right? So this became a big deal for timing analysis. So I got a lot of data from Intel. They wanted to find a long pass in their false pass in their circuits. These are just function units in their chips, and they enumerated them for us. They wouldn't give us the actual chips, but they gave us paths. Here's a path. Here's a path. Find me any of these are false. We found almost 100% of them being false, but that doesn't mean the chips were bad. They were giving us short paths that were false, not the longest path. The longest path rarely was false. Okay, so that was the end of that. A year later, this made the New York Times and the Evening News, the separating the unsolvable and the merely difficult. If you remember this is the phase transition business of random SAT. So the idea was, SAT problems can be characterized by close to variable ratio. And there is a phase transition that happens, when you reach about 4.5 or 4.25 clauses per variable. Well, our problems were very large and they didn't have this behavior. So we crashed this workshop on satisfiability, which was held in 2000 in the Netherlands, that was full of theoreticians discussing this phase transition. And okay, so here we were, young and beautiful back then. And we told them, our problems do not have this behavior. And we need your brain power to try and understand why we are able to solve 100,000 variable problems. And you can't solve 50 variable problems because they have a phase transition. They almost kicked us out, but I'm glad to say that persistence made it possible for us to kind of invade that little group. And now we have a bunch of practitioners and theoreticians working together. A year later, this is kind of going very fast here. A group of people at Princeton took our graph and profiled it. And they found where the bottlenecks were, and the bottlenecks were in figuring out when a clause becomes unit. So they came up with an optimized BCP procedure using a so-called two-watch literal structure. And they had essentially a conflict-driven branching heuristic called VSIDS. So that became called conflict-driven clause learning, or CDCL, okay? This is kind of a capsule history of how this thing happened. So, and then a year later, a 700-line C++ program called Minisat incorporated all of these things. There are other things that happened. I'm just being brief over here to just give you the big idea. Highlight here, this is Martin Davis. This is 2007 SAT conference. And, you know, it's very rare that you meet heroes, but, you know, it was very nice to meet him. I met him some other times later. You know, he's a very nice guy. His wife is a nice lady who is an artist. And this is the culprit, you know, Joao Paulo Silva, the student who did the graph work with me, and his wife, Inish, who is also a SAT practitioner. It runs in the family, it seems. I'm going to skip this because I'm running out of time, but I can tell you later if you want. The postscript of this is that timing analysis of VLSI chips was the catalyst for, but not the beneficiary of the development of CDC LSAT solvers. The CDC LSAT solvers enabled, on the other hand, the development of powerful satisfiability modular theory solvers like the C3, YIKES, MathSat. They also allowed the development of automatic incremental induction model checkers like IC3 and PDR, and the development of new proof complexity insights. I just received a chapter from somebody that wrote me a nice note that 10 years ago, a theoretician implored him to really look into why CDCL is working so well on structured instances, and maybe some more. So the moral of the story is timing analysis is what led to CDCL. Then we got, you know, kind of a little follow ourselves, and we said, can CDCL be improved further? Can we make it faster? Can we do more? And here's an idea. If the search tree kind of looks like this, I have done some search and I got to a subtree and I found no solution in that subtree. And then I'm searching somewhere else in another part of the tree. And for some reason, I know that these two subtrees have some symmetry. Okay, if I knew that the left one did not have any solutions, can I then infer without doing any work that the second one doesn't have any solutions? Seems like a great idea. Involves symmetry. What did I know about symmetry back then? Very little. Okay. We were inspired by a paper by Crawford and Ginsberg and Lux about breaking symmetry in big SAT instances. So what does that mean? Okay, you take your CNF instance, you somehow turn it into a graph, and then you find the symmetries in the graph implemented as symmetry generators. You convert them into symmetries of the formula, and then construct so-called symmetry breaking predicates. These are things that will block out symmetric assignments in this space. So, you know, instead of searching in the 2 to the n space, you search now in the equivalence partition of that space. And then you pass this on to a SAT solver, and that would, you know, I said, fantastic. You know, I had a colleague here who knew about group theory. I didn't. And he said, we should do this. And I said, okay, we can turn it into a graph. I don't know how to do find the graph symmetries. We figured out how to do the symmetry breaking. And the only thing that we needed was, how do we do the graph symmetries? And said, okay, there's a program called Naughty. It can do that for us. So just the graph symmetry, I mean, turning the formula into a graph was trivial. You have two kinds of nodes, vertex nodes and literal nodes, and each, closed nodes and literal nodes. So clause 1 is A or B, clause 2 is not A or not B, clause C is just C, and then you put edges to connect these literals to make sure that Boolean consistency is preserved. It's a bipartite graph. We pass this on to Naughty. Let's do that. So I didn't know anything about Naughty, and so here is a discussion with another student. I said, do you know Naughty? He said, because we need to use it to run Naughty on the graphs that we create from CNF. And the student happened to be a math major. He said, yes, I had it in a math class. We'll do that. And then he came back and he said, it doesn't work. He said, the graphs that we're sending to it are too big. So I asked how the graph represented. Can you check into the source code? He came back and he said, it uses a dense incidence matrix. I said, but our graphs are very sparse. Can you modify Naughty to just use an adjacency list instead of a incidence matrix? Just go inside and change the data structure for the graph. He did that, and then it ran. So let's publish. We published. That was our first foray into publishing on symmetry detection in CNF. We were able to take very large graphs. You can see the number of vertices over here and the number of edges. And here is naughty and saucy. Saucy beats naughty hands down. Speed ups are out of the world. And in terms of, are we actually benefiting from doing this? Well, it's a mixed bag. We're using the Z-chaff solver to do it with and without symmetry. So without symmetry, I'm sorry, with symmetry, it wins in many cases, but sometimes it doesn't, okay? And sometimes it times out. But, you know, we're getting like orders of magnitude speed up in some cases. So now we're getting the reputation that we are experts on symmetry breaking and symmetry discovery and so on. And so I'm asked to write a chapter on symmetry and satisfiability for the handbook on satisfiability. And at that time, I was at Carnegie Mellon in Qatar. So my student was in Chicago, I was in Qatar. I panicked because I needed to write something about symmetry that I didn't know. The only thing we did with Naughty was just to change the data structure for the graph. So I asked the student, do you understand Naughty's algorithm? And he goes, yeah, a little bit. It's not easy to explain. I said, okay, can we trace its execution on a simple graph, kind of reverse engineer it a little bit? So he said, okay. And then he explained it to me. And I said, okay, now I know what it's doing, but why is it doing that? He said, well, because it's actually solving the canonical labeling problem. I said, what the hell is that? I didn't know anything about that. I thought it was finding the symmetries, the graph automorphism. He said, well, they are related problems. I started thinking, this is the wrong tool for what we want. So I told him, I see a much simpler way to solve the graph automorphism problem. Why not create a permutation search tree analogous to the Boolean assignment search tree in SAT? And he said, oh, that's a great idea. But meantime, I had to finish that stupid chapter before we do this. So I did the best that I could to pretend that I know how Naughty works, to write that chapter and to write the symmetry breaking and all of that. And it got published. But then a little later, it got published a year later, but you know, a little later that year, we managed to actually find another implementation of Saucy that now not only took advantage of the sparsity of the graph, but of the sparsity of the symmetries in the graph. And we, the key idea over there was the notion of partial permutations, which I'm going to tell you about. Partial permutations instead of complete permutations. Okay. At that point, you know, we are not only beating Naughty, but we're beating our earlier Saucy. You know, we're getting delirious over here. I mean, this is great. You know, we are, you know, 6 order of magnitude speedups, things like that. I've never done anything that had that kind of performance improvement on anything. So this is great. So I want to tell you now about how we did that, okay? And to show you the issue of stupidity, because I don't know anything about group theory, and I want to now solve a problem in group theory that I knew very little about. So we're going to talk about permutations. And if anybody doesn't know anything about group theory, don't be ashamed to ask, or if you know more than I do, correct me if I'm wrong. So we have a set of numbers 1 to n. Think of them as vertices of a graph that has n vertices. And the permutation is basically a bijection from V to V. We can represent those bijections either in tabular notation or in cycle notation. And a graph symmetry is a permutation that preserves the edge relation of the graph. It's an invariant of the graph. So if you have 2 permutations, gamma and eta on V, we can compose them using function composition, right? We can apply eta to V and then apply gamma to the result of that. And so what is a permutation group? Well, it's a structure G and this permutation composition operator. G is a non-empty set of permutations that is closed under function composition such that the composition operator is associative. There is an identity permutation, which I'm representing now with open bracket, close bracket. Basically, it maps each vertex to itself, its identity. And every permutation has an inverse. So pi has an inverse, pi inverse, such that if you compose it with its inverse in either direction, you get the identity. Now, we're all probably familiar with the symmetric group on an M element set that I'm calling S sub M of T that has n factorial permutations in it, right? N factorial rearrangements of the elements of the set. So let's talk about what a graph symmetry is. And I'm gonna show you at the end, we're gonna how to solve this graph with Saucy, right? So it's got it's an 8 vertex graph, okay? And let's talk about some permutations of the vertices here. So this is in cycle notation. In cycle notation, what we're saying is if 1 and 4 are swapped, so 1 becomes 4, 4 becomes 1, and simultaneously 2 and 3 are swapped, that's a permutation of the vertices. Let's apply them. So 1 becomes 4 and 4 becomes 1, 2 becomes 3 and 3 becomes 2. Everything else stays the same. So 5, 6, 7, 8 stays the same. You compare this relabeled graph with the original one, and you notice that it's identical if the set of edges is unchanged. So we say this is a permutation that is a symmetry of the graph. If, on the other hand, I try this permutation. Now, this permutation is a little more complex. There's a rotation it's a random thing. It's not a rotation. It says vertex 1 becomes 2, vertex 2 becomes 3, 3 becomes 4, and 4 becomes 1. Okay, that's one permutation. And 5 and 6 swap. So if I apply this to the graph, it goes like this, and 5 and 6 like that. Now this graph has edges that are not in the original graph. There is no edge between 2 and 6 or 1 and 6 in the original graph. So this graph is a different graph. So this set of edges is not the set of edges is different. This is not a symmetry. So what we want is out of the 8 factorial permutations, figure out which ones are symmetries and which are not. Is that clear? If I pause here for any questions so far? Okay. Now, to talk about permutations, we need to talk about partitions. So a partition is simply just a set of subsets of a set that are mutually exclusive, and their union is a set, except now we place an ordering on them. So the vertical bars over here is like, partitions in a building, like apartments. So we have M apartments over here, where W1, W2, etc. are subsets of the set of vertices V that we saw before. And we can have many different partitions, okay? We're gonna call these ordered partitions. So OP is an ordered partition. If the number of cells in the partition is 1, then we have what's so-called the unit partition. And if the number is equal to n, then it's a discrete partition where every cell has a single element in it. So it took me a long while to understand canonical labeling. These papers are extremely difficult to understand for people who are not deep in that subject. But here is kind of my way of explaining what canonical labeling means, okay? So we start with this very simple graph, 3-vertex graph, 1, 2, 3. There are 6 permutations of 1, 2, 3. And this is if you will, a partition ordering tree, or order partition search tree, I should say. We start with the unit partition 1, 2, 3 in one cell, and then you break them up into several cells. The leaves over here are discrete partitions. So in this partition here, 1 is in location 1, 2 is in location 2, 3 is in location 3. Here, they are in different locations. So they do this, and then they say these ordered partitions implicitly describe permutations. So for example, the left one over here is the unit permutation. So 1 maps to 1, 2 maps to 2, 3 maps to 3. This one here, it says 1 maps to 1, but now 3 is in location 2, so 3 maps to 2, and 2 is in location 3, so 2 maps to 3. So you get the swap, 3, 2, and so on. They do this. And then they said, okay, let's now label the graph with these permutations. So if you label them, this is the original graph doesn't change. This is 3 and 2 got swapped. This is 1 and 2 got swapped, and so on. So these are all 6 different labelings of the graph. And they want to find a labeling that they can consider to be unique or canonical. Different formulas or different functions for canonicity. They say, let's make a list of the edges and order them lexicographically, okay? And find the greatest lexicographic ordering. So let me show you what that is. The edges over here are unordered, or bidirectional. So we start with the higher index and go to the lower index. So I have an edge from 3 to 1 and from 2 to 1. So the string that describes this initial configuration is 3, 1, 2, 1. Similarly for this one, it's 3, 1, 2, 1. In this configuration here, the edges are 3, 2, and 2, 1. This one here is 3, 2, and 3, 1. So you start now, you're looking for the maximum string that characterizes a labeling. And that turns out to be this one here, 3, 2, 3, 1. And you can see that these two that I highlighted here are identical, except that one of them is flipped on the horizontal axis, but it's the same graph. So they consider this to be the canonical label, the canonical isomorph, which is obtained by having this labeling. The problem is, as you see, the things that are symmetric have the same label. And if you have a lot of symmetries, then while you're searching for this canonical label, you have to prune out those symmetries. Otherwise, your search tree becomes extremely huge, especially that you need to go to the leaves. Okay. So the basic insight was, we are not, at that point, we did not understand canonical labeling. We were just looking for the symmetries of the graph. So why can't we just look for the symmetries instead of looking for a canonical labeling? The insight was, here is a set search tree on 3 variables. Each node represents a partial assignment, which you can think of as a set of assignments. The top node, there are no assignments to the variables, so it encodes 8 possible assignments implicitly. You go 1 level down, you assign x to 1 or x to 0, and now there are only 4 different possible values of y and z left. So these 2 nodes in the second level represent 4 possible assignments, and so on and so forth, until you get to the leaves when you get complete assignments. Can we do something similar in the space of permutations? I just want to be able to say, I began with 3 things, 3 vertices. Okay, 3 vertices give me 3 factorial, or 6 permutations. I want to have a representation for that is compact. And then when I fix one of those vertices, so I get to the next partition that has, the top one is the unit partition. Now I go one to has 2 cells. One is a singleton, the other has 2 things. Now this has, each one of those is 2 permutations, 2 factorial permutations. And then when I go to the bottom here, I have 1 factorial permutation. Is there a way to kind of do something similar? So now we are in the space of permutations. And the answer is yes, we can do this. And what we need to do is have another ordered partition at the bottom, okay? So we're going to talk about an ordered partition pair, okay, where we have a top partition and a bottom partition, both ordered. And we can then discuss the different varieties of this. So the isomorphic OPP is one where the top and the bottom partitions have the same number of cells. So number of cells is the same, and the cardinality of each cell is the same. That's called isomorphic. I'm going to give you examples in a sec. If you negate this, either the top and bottom have different number of cells, or if they have the same number of cells, but some cells have different numbers of elements in them, then we call it non-isomorphic. An isomorphic could become matching if, in addition, for non-singletons that are equal in size, their content is the same. Not only are they just equal in size, but they have the same content. We call that matching. And finally, unit and discrete means unit top, unit bottom, and discrete top, discrete bottom. I'll give you an example here. So this is like the tabular representation of permutations. If I have a discrete OPP, like this one here, you can read it as I am mapping 1 to 3, 3 to 2, and 2 to 1. Okay, so domain is the top, codomain is the bottom. That's encoding 1 permutation, which is 1, 3, 2. If I have a unit OPP, well, in this case, I can actually represent all 6 permutations on 1, 2, 3, because what can I do? I can either map 1 to 1, 2 to 2, 3 to 3, which gives me the identity. Or if I say 1 goes to 2 and 2 goes to 1, that means 3 maps to itself. I get the swap of 1 to 2. You keep going down the list here. If I map 1 to 2 and then map 2 to 3, then 3 must map to 1 to complete the rotation. And I get 1, 2, 3, and so on. So this OPP, unit OPP, is a representation of all 3 factorial or 6 permutations implicitly. This is an isomorphic OPP. It requires that 3 map to 2, but it allows 1 to map to 1 or 1 to map to 3. So I get 2 permutations here. 2 to 3, 3 to 2, and 1, 3, 2. And this is a matching OPP. Notice here now that I have identical number of cells top and bottom and identical cardinalities, but the one that is non-singleton has the exact same elements, 1, 3, 5. That means the number of permutations here is 2 maps to 4 and 4 maps to 2, composed with all 6 permutations in 135. So this has essentially 6 permutations that are the composition of 2, 4, and all 6 permutations 135. And finally, here is a non-isomorphic OPP. The number of cells top and bottom are the same. Remember, this is ordered, but their sizes are different. There is no way I can make a permutation out of this. So this conveniently represents the empty set of permutations. Okay? So let's apply this to a simplification of this graph. I'm going to start it with something simple. So I'm going to just take the same 3 vertex graph that I had before, except this time they're numbered 6, 7, and 8. Okay. So we begin with the unit OPP that represents all possible permutations, all 6. And now we start thinking about making assignments. It's like assignments in SAT. Any vertex in the top can map to any vertex in the bottom. So we have choices. So I'm going to choose 6, and I say I'm going to map it to, it has 3 choices. The branch gain factor here is 3. So map it to 6, 7, and 8. But I'm going to randomly start to map it to 7 here. Okay, so if I say map 6 to 7, okay, then I separate it from the top and bottom. And in the top, I have only 7, 8 in the first cell and 6, 8 in the bottom cell. I need to continue mapping. So now 7 can map, or here I'm choosing 8. I can map 8 to 8, and I get a discrete partition. Okay, that discrete partition does the following. And I look at this, and it looks like it's not isomorphic to the original graph. Okay, so it's not a symmetry. Is that clear? And you can tell that because 7 in the original graph, had a degree of 1, and here in the other one it has a degree of 2. So it's incorrect. It's not a symmetry. I cannot swap 6 and 7. The other mapping of 8 is to go to 6, and it also is not a symmetry. Okay, so we finish this branch. Now let's map 6 to 6. Now I can map 7 to itself, or 7 to 8, or 7 to itself, and these are both symmetries. And then I can map 6 to 8, and then try. So you see how this is going. This is like essentially like SAT, except that our assignments now are mappings from top to bottom. And you can see here we did a lot of work, but we got the 2 permutations, the identity and the fact that we can swap 7 and 8. Now, we can improve this with vertex partition refinement, which is analogous to Boolean constraint propagation in SAT. Okay, so we can distinguish vertices that have different degrees. 5 has degree that is way higher than the other vertices. It cannot map to any other vertex. So we keep a vertex neighbor count, and we use it to partition. If we just go by degree, we can split 5 from all of the others, right? Can split 5 from all of the others. We repeat this, and so now each other vertex has 2 blue neighbors and 1 red neighbor, right? And this becomes stable. This is called an equitable partition. This is like Boolean constraint propagation. What is the effect of a decision that we made? Actually, there's no decision over here, but you'll see later it's going to be a decision implication. Okay, and so we go from this OPP, which is the unit, and through a process of refinement, it splits 5 from top and bottom. So if we do this now for this example again, you will find that we can solve it very quickly, because 6 has degree 2 and it splits from 7 and 8 immediately. And now the only thing that is left is 7 to 7 and 7 to 8. And I don't run into any conflicts in this example. Now, let's go back to the original graph, which we're going to solve. And we said, OK, the first thing we do is separate 5. And now I don't know what to do with the rest of it. The first cell has 7 vertices, top and bottom, and they're all equivalent in some sense. They have the same degree neighbors, the same tuple of neighbors. So I have to make a choice. I can take one of these vertices on the top and try to map it to every possible vertex on the bottom. I'm going to take 1 and try to map it to 2. That's like a decision assignment. Let's map 1 to 2. That means I'm going to take it and separate it into its own cell. But then everything that is a neighbor of 1 in the top has to be distinguished. And so what happens is 2 and 3 in the top are distinguished from 4 now, because they have a green neighbor. The bottom also splits because 2 now is separate. I mean, 2 separates 1 and 4 from 3. So we get this partition here, which is isomorphic. That one decision making 1 to 2 simplified, the OPP into this. Keep in mind that when we started, the set was 8 factorial. It represented 8 factorial permutations. The implication on 5 reduced it to 7 factorial because 5 cannot map to anything but itself. Once we make the assignment 1 to 2, now we have many fewer permutations. 6, 7, and 8 is 6, and 2, 3 is 2. This here represents only 12 permutations. A huge reduction. Okay. Now, if I try to do 1 maps to 6, okay, and I do the refinement, okay, now the top and the bottom refine non-isomorphically, okay, which immediately tells me that this mapping is a conflict. I cannot have a permutation that will respect this decision, okay? 1 to 6 does not lead to a permutation. Okay, now, a little kind of foray into group theory, which I hope will not be too confusing. One of the major things in group theory is that you can represent the order of the group, not by listing every member, because that is actually quite large, but you can represent it with a small set of so-called redundant generators. I'm going to show you what those generators are. So, since 5 cannot map to anything, the square has 8 symmetries, okay? Just take my word for it. These are the 8 symmetries, the identity, and then some reflections, north, south, east, west, north, east, southwest, and so on, and some rotations. And the triangle has 6 symmetries, and they're independent. So with 8 vertices, we have 40,000 permutations, but this graph has only 48 symmetries, which is 8 for the triangle, 8 for the square, and 6 for the triangle. And so we cannot enumerate 40,000. We want to get to actually the 48, but we want to actually get much less than 48 as well. So I'm going to just tell you here that these 4 permutations generate all 48 permutations. I'm going to show you how. So these 4 permutations are a simultaneous swap of 1, 2, and 3, 4, and a swap of 2 and 3, and swaps of 6, 7, and 7, 8. These 4 permutations, if you compose them in all possible ways, will end up with 48 permutations that are symmetries of this graph. That's what we want. We want to find these. Okay, so the symmetry group induces an equivalence partition on the vertices called the orbit partition. So what the orbit partition says basically is if vertex I is equivalent to vertex J, it means that means they're in the same orbit. That means there is a symmetry that maps I to J or J to I. So we're going to start with an initial partition that says every vertex is its own cell in this partition, meaning I don't know anything about the symmetries. If you do degree refinement, you split 5 because you know that 5 cannot be symmetric to any of the others. Right? But degree refinement by itself is not enough, so we have to make some decisions and implications. I keep pushing the wrong key here. And so at the end of our process, we want to get to this orbit partition up here, which is 1, 2, 3, 4 are symmetric to each other, and 6, 7, and 8 are symmetric to each other, and 5 is not symmetric to anything. That's the end result of our exercise here. That's the orbit partition. So we want to go from the initial partition to the orbit partition. That's what we want. Now I'm going to have some notation over here. The group is called G. So G3 is a name for the orbit of vertex 3. The orbit of vertex 3 is the cell in the orbit partition in which 3 exists, which is 1, 2, 3, 4. So this is what it's just a bit of notation over here. So the orbit of 3 is the cell 1, 2, 3, 4. And its size is 4. Its order is 4. Cosets. So we need the notion of a subgroup of a group. It's a non-empty set of the group that is closed under binary composition. And it must include the identity. Otherwise, it's not a group. So it's a subgroup of the larger group. And a subgroup partitions the larger group into so-called cosets. Okay, we're going to see what cosets in a minute are, such that every coset has the same number of elements as the subgroup H. Finally, we need only one representative from each coset to generate the entire group. So we don't need all of the elements of a coset, just one element. If you compose it with the subgroup, you will generate the entire subgroup, entire coset, and that is sufficient to generate the entire group. I said that in a very clumsy way, but the point of it is, we're going to see in a little bit, is that the structure of our permutation search tree is going to look something like this. We're going to begin by doing so-called subgroup decomposition. So I'm going to start with everything, and then I'm going to pick a vertex and map it to itself. So I'm going to get a subgroup C, I'm going to call G sub I. Okay, this is fixing 1 to 1, for example, and then find implications of that. And then fix 2 to 2, fix 3 to 3. And anyways, just these are identity mappings. This will end up with the identity after some number of levels. These things are referred to as stabilizer subgroups, and each level is called a stabilizer. After that, we have to actually start kind of looking at other assignments. So we start from the bottom, we map K to K, so we must map K to something else, right? So, you know, K has to map to something else in its orbit, in its cell in the partition, and so on and so forth. So these other assignments are the cosets, of the things on the orange branch. I'm going to show you just an example of that here. So in the stabilizer level at J, if I then map J to another vertex called J1, I might get a coset called H, and I want to find a symmetry in that tree, in that part of the graph, in that part of the tree, I should say. So if we find one, like there is a permutation J to J1 that is a symmetry of my graph, I can stop. I don't need to do anything more, because I know that if that is the case, then there are exactly that number of permutations that are also symmetries, and they are the same size as the size of the subgroup G sub J. So this is like SAT. I need to find one solution. I might also end up with finding nothing. Okay, that means this mapping J to J2 is not a coset. Okay, there is nothing there. Here's another one. So that's what we're going to be doing. And we're going to be using some of this to prune the search. So we're going to do recursive subgroup decomposition and then search for coset representatives, which is surprisingly like SAT solving. And we're going to prune in two possible ways. One is coset pruning, which is once I found a representative in any coset, I'm done. I don't need to do anything more. That's group theoretic. And orbit pruning, which is once I found something and it's in the orbit of what I found, I don't need to do another mapping. The contribution that we did was the algorithmic pruning because of the OPP data structure. I'm going to show you what those are. There are two of them, matching OPP and non-isomorphic OPP. So, fasten your seatbelts. We're going to execute saucy now on this graph. Okay, we begin with the unit OPP. We do refine, which splits 5. And now we have to do the subgroup decomposition. So I'm going to take 1 and map it to itself. That means I'm going to take 1 and split it from the others, and then see if I can refine. And here I can refine as follows, right? So we split 1 from the top, 1 from the bottom. They're going to refine identically now because we're mapping identical vertices to themselves. Okay. Now what do we do? Okay, we can choose any member of a cell that is non-singleton and map it. Here I'm just arbitrarily going to choose 6. I'm choosing the smallest cell to keep the branching factor small. So 2 can map to either itself or to 3. I'm going to map it to 2. And if I do this, I get this OPP. There is no refinement necessary over here. Then I map 6 to 6. I get this OPP, map 7 to 7. and I end up with the identity. Okay? So now this is my first stabilizer group, which is G7. Its cardinality is 1, its order is 1, there is only the identity. Okay? And I can then go and say, what's the other mapping that I can do here is I need to map 7 to 8. And if I map 7 to 8 and check it, is it a permutation? Is it a symmetry of the graph? It turns out it is a symmetry of the graph. And so I can merge 7 and 8, the orbits, to get this orbit 7, 8. I'm done here. But now what I can do is I can determine the size of the orbit of 7, which is 2, right, at this point. And I can then compute the size of the subgroup at 6, which is Z6. This is a group theoretic computation here. It's the order of the subgroup of it times the size of the orbit of the variable that was used to make that subgroup. So it's 1 times 2, which is 2. And you can see that subgroup G6 has 2 elements, the identity and 7, 8. But then we have to map 6 to 7 and 6 to 8. So let's do 6 to 7 here. It splits like this. And there are choices here of what to do, but I'm skipping over this just to give you the big idea. So we try to, if we do 6 to 7, we try to do 7 to 6 to keep the permutations sparse. Okay, so we do 7 to 6, and it turns out to be also a permutation of the a symmetry that's a permutation of the graph, or a permutation that's a symmetry of the graph, and we can then join these to get the orbit 6, 7, 8. At this point, I don't need to do any more. This coset here has a solution, and I can prune here by coset pruning. I don't need any other solution here. Because 7, 8 can be found, I mean, the other permutation, which is 6, 7, 8, can be obtained from the other 2. And I can prune this one, 6 to 8, because 8 is already in the orbit of 6. And so I can stop. So now we can compute the orbit of 6 is size 3. And so the size of the group at this level here, 2, is 6, 2 times 3. The other mapping I need to do is 2 to 3, as you can see, because the cell that 2 is in has 3 at the bottom. So if I do 2, 3, now I have a matching OPP. The only non-singleton that has that I have here, 6, 7, 8, it's identical top and bottom. And so one of the things that is a permutation in 6, 7, 8 is the identity. Since I can either find many solutions or no solutions, if there is a solution, the identity on 6, 7, 8 should be enough. If it's not, then there is no solution. So I can stop here and say, try this permutation, swap 2 to 3. And if it works, then we don't need to do anything more. This alone was the reason for getting 5 or 6 orders of magnitude to speed up over naughty. Because remember here, we're not talking about 8, we're talking about 100,000 vertices or 1,000,000 vertices. Okay. So now we can join 2 to 3, and we can then go up. Now the order of this group is 12 because it's 6 times 2. I map 1 to 1. I need to map it to the others. I map 1 to 2. Okay, I get this. I map 2 to 1, which refines like this. Then I map 2 to 1, and I get this, right? Now this is also matching, okay, but it's a more complicated permutation. It is 1 to 2 and 3 to 4 simultaneously, right? So I can now merge the orbits and I get 1, 2, 3, 4. We're getting there. Now I can avoid doing 2 to 4 because I already have a solution in this coset. And I can prune the remaining ones because 3 and 4 are now in the orbit of 1, right? I don't need to do them. I map 1 to 6, and we did this before. This is the case where it mapped non-isomorphically. So I know there is nothing to do over here. There is nothing to do. And I look at the other orbits of 6, which is 7 and 8. Since I cannot map to 6, I cannot map to 7 and 8. And I'm done. And now I can compute the order of the top group, which is 12 times 4, which is 48. And I got the exact same permutation that I was showing you earlier. 7, 8, 6, 7, 2, 3, 1, 2, 3, 4. We get other permutations if we did choices differently. But that's the idea. Any questions about this? I like this so much, that, because it's so easy and so simple. So here's how it works. We're looking at vertices.
I have a question.
Yes.
So what is the complexity of all that?
So the number of, what this guarantees is the number of permutations that you get, the generators, has to be less than n-1. Has to be at most n-1, where n is the number of vertices. That's the maximum number of generators that you get. A more detailed analysis of complexity I am not aware of here, okay? All I can show you is empirical results. I'm not a theoretician, Rina. I'm a algorithmic guy. So here you see 10 million vertex graphs are done in less than 10 seconds, okay? There is about 1,100 formulas over here that we did, and you can see that it timed out on 18 benchmarks here that were crafted benchmarks. So it's obviously, we can't claim, we solve the world, So, but, out of 1,100, we finish in most of them in about 10 seconds we finish. So it's very fast. The order of the symmetry group is amazing. There is one here that I didn't plot. The order was 10 to the power 142,761. We can compute the order of the group, but we cannot actually list anything. And you see those red ones here are the random benchmarks. The random benchmarks have no symmetries except the identity. This is why this business of doing random is not helping us, for practical set. Now, let me show you the bad news. The bad news is when we do this and try to figure out if adding symmetry breaking to SAT will help. Sometimes it helps, sometimes it doesn't help. It's basically meh. So again, we end up with solving a problem that we didn't start solving to begin with, and we end up with a solution to another problem, which is finding symmetries very quickly. In fact, we were able to actually solve the canonical labeling problem by a clever combination of a canonical labeling tool, Bliss, which, by the way, took some of our ideas and put them in there, but it's a canonical labeling tool. What we did was to say, let Bliss run and find the sequence of stabilizers, pass them on to us. We'll then give you the orbits at those levels, and then you finish. So now the canonical labeling tool does not have to search for symmetries, and now we are faster than it. So we are able, by solving the symmetry problem separately from canonical labeling, make the canonical labeling problem finish quickly. I see I'm running out of time. So lots of people helped me with this. These are some of them. The SAT work was done by João Marques Silva. The symmetry stuff was done by these other people, because I had to learn a lot about it from my mathematician colleague, Igor Markov, who is no longer with us. He's at Facebook now, I think. They pay a lot more than Michigan, I think. The others are with Amazon and Wesleyan Illinois University. So I want to finish by reading the last sentence in this thing, which is that the more comfortable we become with being stupid, the deeper we will wade into the unknown, and the more likely we are to make big discoveries. And I can't, I go by this Bible here. I mean, I just go into things that I don't understand and try to understand them to the point where I'm surprised by what we get out of the understanding. And with that, I will stop, because I think I've taken more time than I should.
Thank you very much. Any questions? Yeah, Bobak? No, okay.
I'm sorry, I think I probably went too fast. I was debating whether I should put both the SAT and the symmetry stuff in one talk. And I think the verdict is that was a bad decision.
So I have a question. So you mentioned early on this this phase transition work, right? And so there's a question of, so why are the predictions there not representative of these problems? And there's the superficial answer, which is that, well, random instances look different from structured instances. But I guess my question is there a step deeper of understanding there? Is there any notion of like, what are the types of patterns that show up in the real instances that are distinct from these random instances?
This has been kind of the holy grail of trying to understand why CDCL solvers work on instances that are structured in some form. Things that describe things that humans create, right? And so there is a progress that has been made on that. There is the sparsity of the constraint system. There is the fact that you may not have the self-similarity, some of that is there. All I can tell you, Eric, is that I just received a chapter in the next edition of the Handbook on Satisfiability that talks about advances in proof complexity that describes what the how the CDCL set solvers are able to actually solve these. So we're not talking here about worst case, we're talking about average case. So we're trying to understand what is it about these things that makes them easy to solve versus things that are less structured. Okay, I think structure focuses the search and doesn't make it meander into places where there are no solutions. But beyond that, I think we still need some more. I haven't read the chapter, he just sent it to me. This is a fellow that I met at MIT about 10 years ago, and he just was nice enough to tell me the other day that on a walk back from the seminar room, I beseeched him to really think about understanding why. And he said, you set my direction in academia, and he sent me the chapter. I haven't read it yet. I just got it about a week ago. But I think, the theoretical understanding of, I know that mathematically it's hard to do this. Random is easy to describe mathematically. Structure, there are many types of structure. And how do we describe this and come up with, conclusions? I think theoreticians find that very hard to do.
I have a simplistic hypothesis. I think that it's possible to make a connection between closed learning and the tree width of the graph. So if you are generating all the prime implicates of a theory, it's related. I mean, the size, the number of, it's like generating all the possible clauses that you can learn from a given set of clauses. So, and it's if the problem is sparse enough, you can end up with a relatively small set. And if it's completely uniform, it can generate something that is completely complex, and maybe it's related to that.
So yes, actually that was one of the things that the original Davis-Putnam procedure was actually generating all implicates, if you will. It was just solving the problem, right? And so what CDCL does is it says, if you have all the information, then you don't need to do search. But all the information is exponential. If you do not do implications, then you're not learning anything. Then you search in the futile pit. So this is like, it's just about right. You learn only what you need, right?
Yeah.
It's a good way to think about it. It doesn't explain why it works in practice on large problems, right? There is more to because this doesn't work on random. I mean, you can give me a small random problem, and this idea still doesn't work there. Because the search space is exponential. And so if there is no guidance in the search space that says, okay, because of something I know about the structure, you can prune out a whole bunch over here. Random doesn't give you that. Random, right, at the phase transition doesn't give you that.
Yeah, I have just one more question. To what extent the symmetry breaking that you described is playing a part in current SAT solvers?
Not very much. This is one of those things that I was very frustrated with. So when you do the symmetry breaking, you do it by ordering, by static ordering, so you need to create some predicates based on a static ordering. The solver is working with dynamic ordering. So you learn really good symmetry breaking predicates, but they don't get used. And so the idea, why not do it dynamically, right? when you do it dynamically, even though saucy is very fast, and we integrated it with a solver, once you put it in the inner kernel of the solver, the gain that you get is more than offset by the overhead of doing it. So it didn't work. I'm still kind of thinking that it should work at some point. Sometimes you get implied symmetries when you start with something that's not symmetric, but after you make some assignments, it becomes symmetric. It's inconclusive, Rina. I don't understand why it's not working. It is not working. That's all I can say. You know, Symmetry is working, by the way, on something else that we're working on, which is unbounded protocols. Symmetry is working very well on those. But I'm not ready to talk about that yet.
Any more questions? Okay, thank you very much. Fascinating. Very interesting. Thank you.
Thank you all very much. And I apologize for going over. Thank you.